or somebody on the Zoom meeting, can you just confirm you can hear my audio, please?
Yes.
Perfect. Thank you. So everyone, we all got MTP sync clocks, right? So as soon as my computer says 5:15, which is in 35 seconds, we'll get started. So thanks, everyone. Glad you can hear me, and I'm looking forward to giving the presentation. 25 more seconds, gang.
In that 25 seconds, I would like to really thank you, Kevin, for your time. This means a lot to all our students, and we're excited to hear from you.
Thank you, Rajshri. And just for your students, it looks like the program or lineup you have presentations looks very interesting. And, you know, I'll say to all the students, I have some research. A lot of the other faculties got super cool research too. So hopefully you'll find some opportunities to participate.
Definitely.
All right, gang. I'll go ahead and get started. Go ahead and punch record, Rajshri.
Okay. Thank you. And congratulations as well. We're recording.
Okay, hello everyone. Thank you very much for joining this evening. I'm Kevin Gifford. I'm a research professor in computer science, and I'm excited to kind of overview some work. It's always fun to talk about the stuff you're doing because we always think the stuff we're doing is the coolest. But really, you guys, I'm going to overview this. You can tell I've got 17 slides here, so this will probably take a half an hour. And you know, at the end, I'm going to tell you about several opportunities you have to potentially work with me. And this applies to other faculty as well. I happen to have several openings right now for hourly researchers, for people that are doing MS thesis or independent study, and for GRAs on these spectrum-related activities, everyone. Okay, so opening that graphic there. Does anybody know how you produce this data to look back at the start of the universe? It's with radio astronomy, right, guys? So radio astronomy are the huge telescopes, right? You know, there was Arecibo in Puerto Rico. The Green Bank telescope in Virginia is a huge one. I'll show you some pictures of that. But those are just big telescopes that really are listening to the Big Bang, right? Because those RF signals have taken, you know, those 14 billion years to reach to the Earth. And so just by looking at the received energy coming from the universe from back in time, you can figure out what the different stages of the universe were. That's exactly how that works. You know, those big dishes, they're not transmitters, they're listen only. Right? It isn't like those dishes put out energy. They're just collecting energy in certain wavelengths. And typically those wavelengths are for hydrogen or for helium, you know, the first two components after the Big Bang. And so by looking at the energy you get in particular spectral bands, you can make a lot of decisions and understandings about the start of the universe. So super cool stuff. I'm a wireless engineer, you guys, in wireless communications, but for me, I've always been enthralled with, you know, the start of the universe and the Big Bang and how all that information gets figured out. So that's that opening graphic, and that will serve as kind of the basis for the problems I'm trying to solve. So here's the background, you guys. So radio frequency, right? Whether it's AM radio, FM radio, Wi-Fi, right? It's all RF energy, right? And really in the modern world, especially our 21st century, RF spectrum dependent systems are actually critical, right? They're critical to the economy and they're critical to national defense, okay? A couple of little tidbits, right? I mean, everybody's got their phone. Right. And it's at the point where, and I think I could argue for this, that access to the internet is a fundamental human right. Right. So people in, let's say, oppressed or third world countries can get, you know, information freely. And so really, I think it is a fundamental human right. And I'm not going to get into a debate there, but I think anybody would say it's important to have access to the internet. Right. Okay, when was the last time you plugged your computer into an Ethernet cable, right? It's all wireless, okay? And in that regard, you guys, I'm going to take a 10-second tangent and tell you all about the introduction to wireless class, which is CSCI 4200, cross-listed as CSCI 5200, right? And if you guys are CS majors, I would tell you all, my recommendation would be, to have one course on the introduction of wireless, right? Think of how important wireless is in general networking. And so I'm not expecting you to be a double E student, but having an overview of all the wireless communications and how important it is, I think would be good for your career. So that course is actually taught both fall and spring. And so it's something for you guys to think about in the future. So whether it's Wi-Fi or whether it's your cellular phone, we're accessing the internet in a mobile manner over wireless communications. And one thing that is interesting, you guys, is that there is a relationship between the amount of broadband and mobile comms a country, US, Germany, pick your favorite country, India. There is a direct relationship between the amount of mobile broadband and the GNP of every country in the world. Right? It's that important. That's how important wireless communications is. So just wanted to point that out. The other thing is it's used for defense, right? For radars. And of course, if you start interfering with Department of Defense radars, well, certainly you're going to be in trouble. And so that's one of the problems that I want to talk about. And the other thing, you guys, is think about, the satellites that are giving us weather type of data, right? Whether it's on agriculture or fires or weather, think about all the lives that satellites have saved because of our ability to accurately predict hurricanes, right? Really is phenomenal. Over the past 50 years, that technology has really saved, thousands and thousands of lives. And of course, now we got a bunch of new stuff coming, right? Everything's streaming. We're going to have the Internet of Things. We might have the Internet of Things in the ocean. AR and VR is very big. Think about V2X, right? Vehicle to vehicle communications. So the demand for these wireless applications is just exploding. But the problem is that the RF spectrum is a scarce resource, the electromagnetic spectrum. And at this point, in the United States and in most countries, spectrum has been allocated to the point that it's hard to find spectrum for new services. So as a result, you guys, spectrum sharing is very important. It's like cybersecurity, right? For your computers and your networks, you got to have cybersecurity. Otherwise, people are going to hack you and attack you. Well, similarly, there's a similar, let's say, national imperative in the United States, especially, but this applies to the entire world, where we need to use the spectrum better, and that's the the basis of the projects that I do with the National Science Foundation is for spectrum sharing architectures. But really, I wanted to set the problem first, okay? So that is at a high level. Okay, here's the EM spectrum, right? We can go from, essentially DC, right? 0 hertz, and go all the way up to visible light. Now, this isn't the entire spectrum. What would be to the right of this? There would be X-rays and gamma rays over here, right? But I just wanted to show the spectrum up to visible light. And really the thing I wanted to point out, you guys, is, you see where AM radio used to be, FM radio was a little bit higher, right here. All the wireless communication, right? It's at 2.4 gigahertz or 5 gigahertz. It's typically from 1 to 10 gigahertz. So this is where all the, typically the wireless communication services are. That's really all I wanted to show you on this one. Oh, I need to click back on that. Well, I go down. Well, I'm trying to go down, guys. There we go. So this is the United States frequency allocation chart, right? From essentially 3 or 0 kilohertz all the way up to 300 gigahertz in the bottom. Okay. And you guys don't try to read this, just say, holy crap, everything is allocated. That's the message you should get from here. And right here, you guys, this is 2.4 gigahertz, the one that we typically use, and 5 gigahertz would be really right in here. So, all of the spectrum has been allocated. It's licensed. People pay money so that they have got exclusive use to the spectrum. But by getting exclusive use to that spectrum, that can give you some protection from interferers. But the problem is there's no more spectrum, and what spectrum we have we need to share. We need the multiplex, from a computer science networking perspective. We need to multiplex different users across the same pieces of spectrum. So that's the FCC allocation for the United States. Okay, so you guys actually already know a little bit about spectrum sharing, okay? This is our Wi-Fi band, right? 2.4 gigahertz, which is a common Wi-Fi band. The other one is at 5 gigahertz. And the other thing that's in the 2.4 gigahertz band, besides Wi-Fi, these are the Wi-Fi channels up on top here, right? There are 11 channels in North America. There are 13 channels in the EU and Japan, and some people have a 14th channel. But essentially, they're from 2400 to 2480 megahertz as the ISM band. And in that band, right, Wi-Fi and Bluetooth both exist. So do microwave ovens. And then LoRa, which is a type of IoT protocol, exists as well. Okay, so just think about it. Right now, you guys, I'm using my wireless mouse, right, which is Bluetooth. So it's sending out these little signals. And simultaneously, I'm connected to you guys on Zoom over the Wi-Fi channel. Okay. So from this perspective, Bluetooth is able to hop around the Wi-Fi channels that are in use. So that's a type of spectrum sharing. Okay. And so that what we need to do is we need to come up with more sophisticated architectures to enable spectrum sharing across the EM spectrum. But I just wanted to show you, you already have a feel for, potentially spectrum sharing that you utilize. And it used to be, you guys, that, when the 2.4 gigahertz line band first came, widely used for Wi-Fi, microwave ovens were right there. And if you would turn on a microwave oven, then it would your Wi-Fi would be killed. It would kill your Wi-Fi, right? And so what you would like to do is be able to manage. Hey, I can have a microwave oven and Wi-Fi in the same channel, transmitting at the same time, but I'm able to handle the interference between the two different signals. So at a high level, I just wanted to show you that kind of general basis. So how do we look at all of this energy in the radio waves, right? So it's just sensors like sensing temperature, same fundamentals, except, sensing signal transmission really takes a lot of bandwidth. You need to be able to really move some data around. And how you do that is with a software-defined radio, okay? This is this is a quarter here. And so you get the size of the software-defined radio. It's about the size of a credit card and a little bit thicker, okay? And so you take and you hook one of these software-defined radios up to a computer, and actually you can hook it up to something like a Raspberry Pi 4. Raspberry Pi 4 will have enough computational power to bring in all of that data. So what we've done, gang, is we've built a bunch of these sensors with the NSF, and we are deploying them out at radio astronomy facilities to determine the amount of RFI or interference that's coming onto those facilities. Since these guys have the ability to transmit, right? They could transmit Wi-Fi, and then you'd be creating, your own interference. We turn all the Wi-Fi stuff off, and even the electronics that are running on these two boards can produce EMI, electromagnetic interference, or potentially some RFI. And if you're at a site where, like the radio astronomy facility, where you don't want any unintended RFI, then you need to be able to enclose these RFI, EMI generating components in an enclosure, right? It just protects. No energy gets out to the radio astronomy telescopes that are looking for more important things in the sky. So I wanted to show you this. This is a fundamental capability that we built at the University of Colorado. And you guys, the big thing here is these are inexpensive, okay? Typically, people like NIST or NTIA, who do a bunch of stuff in the spectrum, when they go out and measure spectrum, you guys are using, vector spectrum analyzers. You guys, this equipment, typically for one of them is $500,000, so $500,000. Right. So that just becomes problematic because you're just not going to be able to deploy that type of equipment widely. So these sensors here, you guys, actually cost us less than $1,500 to build. And we built them with NIST so that we've got all the proper calibration. We published this with NIST so that people that want to do, radio transmission experiments or radio frequency sensing, instead of having to pay $500,000 for one unit, they can start building multiple units like this at $1,500 a pop, and then really collecting a lot more data. And we've gone to great lengths to, make these very highly accurate sensors. So what type of data do we get in these sensors, and what does it look like? Okay, so here's our sensors here. You guys, here on the right, this is Wi-Fi channel 6. It's at 2.4 gigahertz. 2.4 gigahertz. Wi-Fi channel 6 is actually centered at 2437 megahertz. Okay. And so you can see the frequency is here on the left. So this is going, this is that 22 megahertz channel for Wi-Fi, going from like 2428 up to 2446 here. And when these bands are lit up like this means that you are transmitting data. The brighter these bands, the more data you're transmitting. Now, check out what happened, you guys, when we were looking at this particular channel, and we were doing this for several minutes, but we all of a sudden noticed, hey, we're getting interference at 2447 megahertz. And initially we didn't know what it was, right? But what we did was we were sampling this for several minutes, and we noticed that interference just came on for 1 minute, right? And so what's the obvious observation? Okay, there's a microwave oven near that access point, and that microwave oven got turned on for 1 minute to heat something up. So I wanted to show you guys this because this is really high quality data. And this is the reason we can deploy many of these out in the field and then be able to, help radio astronomy have solid, non-corrupted observations when they're looking back in time. Okay, a couple of other pictures. So same RFI sensors. You guys, we had an access point, and we were on this one, we were looking at 5825, so in the 5 gigahertz range. And we knew that channel was unused, okay? This band had just been legalized, and we had an access point, and we knew that there were no users using that access point. So essentially it was our access point. So what we did was, we used iPerf, right? We set up an iPerf client and a server, and we made that iPerf client push data to the server, okay? This first chart, we're not pushing anything. iPerf is not going. All you are seeing here on these vertical lines, this is the center frequency at 5825. And these lines here are the beacon signals that IEEE 802.11 sends out, to advertise that channel is available. So, a client will see these beacon signals, will know that channel is available, then it just connects to that network SSID. And then once you're connected, then you start transmitting data. And all this is showing you guys, we did this in 1 day with those sensors that I talked about, and we just started pumping up the data rate, right? And what we wanted to show is, hey, we can definitely detect, the changes in data rate sent into an access point with our RF sensors, and we can detect it very accurately. And so you just see this light up from 10 megabits to 20 megabits to 30 megabits. And we actually ran this up to 75 megabits. This curve is really linear. Notice that from 50 megabits to 75 here is an access deal, an X-axis scaling issue. So, my take home lesson here is that we built these really high quality sensors. And, now that you've got the ability to sense the environment, then you can characterize the environment, and you can start to look at doing spectrum sharing type of architectures. So that's kind of the basis, right? I wanted to show you guys the Wi-Fi and Bluetooth that I talked about before. And really, that's why I left this like this. Remember, this is Wi-Fi and this is Bluetooth. So let's look at, I got to find that. So here, you guys, we're centered here at, again, 2437. So this is Wi-Fi channel 6 again. And this is the Wi-Fi channel here, okay? And then you see these little Bluetooth blips, okay? So those are coexisting in the same band. Okay. But what I want to tell you is that with radio astronomy, this is a great example that these little blips would all be interference. Okay. And so that's when radio astronomers are making their observations, they're really looking at the signal intensity in a certain band. A very common one is 1420 megahertz, because that's a resonance frequency band for hydrogen. And so if you look at that resonance frequency band for hydrogen and you're getting the signals, from deep space, you really are looking back in time. And what they don't want when they are doing those observations is they don't want interference, right? Because that corrupts their observations. And this is exactly what the interference would look like from a radio astronomy telescope if they were spanning a certain band, but then getting interference from, let's say, satellites or other RFI that's around the radio astronomy facility. So all done with our sensors, and let's now kind of characterize the problem finally, and then look at how to move forward. So, you guys, the problem here is active emitters disrupt RA scientific observations, and this is important. Radio astronomy is very important, and so is Earth observation. It's the same deal. Those Earth observation satellites are going around the Earth, and they are looking in specific spectrum bands, say for water content or soil moisture or air pollution. They know the RF band that they want to sense. Okay. And so if anything else, feeds into that antenna while they're doing their environmental sensing, then that corrupts their data. And, it makes it either unusable or very inaccurate. So what you want to do is you want to eliminate all RFI or satellite interference for radio astronomy telescopes. Okay, that's the fundamental problem here. And that general problem of being able to share spectrum, if you can do it with radio astronomy telescopes, then you can start doing it with other wireless systems, whether it's Wi-Fi, whether it's cellular. So that's the concept that we're going after here, everyone. Again, I wanted to show you this picture. This is the big Green Bank telescope. Green Bank is in West Virginia. And hey, guys, they actually banned cell phones, and not just on this facility, they banned it in the entire county, right? So they banned cell phones and Wi-Fi in the county that has the Green Bank telescope. The first thing I think about is I think about students and children, having access to the internet, right? I mean, but that's how, they were able to push this through and get it legalized. But honestly, if you were able to share spectrum, you would never have to do that, right? You'd be able to support both the radio astronomy users, and you'd be able to support the cellular and Wi-Fi users, and everybody could happily coexist. So that's, what we're going after. So, if there's a cell tower, near the telescope, remember, cell towers, right, are, the big ones, the macro ones, right, that are doing 4G LTE, the big ones you see along I-70, typically they have a reach on the order of 2 kilometers in diameter. So, if there's a cell phone tower, within a couple kilometers, it's certainly, and really, up to maybe 10 or 20 kilometers away, that dish, because it's so sensitive, is going to see that energy, and it's going to corrupt the scientific observations that the radio astronomers are trying to make. This is actually where we're doing all the sharing, everyone. This is another radio astronomy facility. Looks different than the last one. This is the Hack Creek Radio Observatory, and this is the Allen telescope array. And gang, Paul Allen made his money from Microsoft, but he is a very big technical benefactor, kind of like Bill Gates, quite honestly. And one of the projects that he wanted to do was he wanted to look, back at the start of the universe. And so what they have here is 42, these white dishes are actually the telescopes. And right now they're kind of, they're pointing across the horizon, not pointed up towards the sky. There are 42 of these, they're 6.1 meters, and they can arrange these telescopes in arrays and point multiple telescopes at particular locations in the sky for their radio astronomy scientific observations. So again, on this property, it says when you're going in, turn off all cell phones. And the problem is when people drive to the control center and park out here, Lots of times their cell phones are still on, or their Wi-Fi is on, et cetera. Their computers are on. The computer Wi-Fi is searching for a network to connect to. And actually all that energy hits these dishes, right? So it's not just the cell towers, but even your computers and your handheld cell phones will emit that energy and corrupt those signals. So this is the scenario. So at this facility here, what we are doing is we're implementing our spectrum sharing research. We have our sensors out in the field here. We have one down here at the left, one here in the center, one on the right, one on the control center, and a couple up here. Okay, and they're just our little sensors in their little boxes. They're running all the time. And those sensors, we do different frequency sweeps. Right now, Hat Creek personnel were interested in 400 to 1800 megahertz for some particular science. And so we're just continually scanning from 400 to 1800 megahertz and looking for interference. And if we detect interference, then we alert the operators of the system. And but that's kind of the initial basis of being able to do overall spectrum sharing. Couple more pictures, and then we're going to get to the architecture, and then we'll get to the end, gang. So I wanted to show this again, the problem. Active emitters disrupt RA. So this here, this was at the hydrogen line, 13 megahertz here. And this was from a NASA SMAP satellite that was just sensing in that particular band, okay? And it was looking down at, at the Earth's surface. And you can see all this light up. That's, RF emissions in that 1413 band that is really above the legal interference limit, which is 0.5 Kelvin. Guys, don't get, wrapped around the axle about the numbers here or anything. What I'm showing is that this is a worldwide law about the power level of emissions in that particular band, and it gets, it's exceeded wildly, right? And so all the radio astronomers are saying, hey, we're probably not going to change that situation, but we do need to be able to handle interference. And so again, active emitters disrupt RA scientific observations. And so with spectrum sharing, the idea is to prevent that observation corruption. I gotta get, there we go. So let's kind of summarize, and then we'll show an architecture that can address this. So, overall, you guys, I'm using RA as a particular, high profile example. I think it deserves that level of elevation because of all the science that it's brought us. Also, passive antennas like that, right? That those dishes are just collecting energy. They're not transmitting. That's the same way the Earth observation satellites work, right? They're passive. They're not transmitting. They're just, reading in the RF data at a particular band, again, say it's hydrogen or water, and then making some, environmental determinations from there. So really, you guys, the big thing here is that I would say, in the US, what was this elected? Oh, that was 2015. I can look at that reference. So half homes have cellular. That's probably gone up. I think this here, you guys, this prediction honestly has been updated. I can tell that was Marcus Weldon from Nokia Bell Labs. So that was 5 years ago. The latest update for this is by 2025, 97% of connections will be wireless. So again, you guys, I'll go back to, for all of you, I think that introduction to wireless course is really required for your overall computer networking knowledge. And again, it's taught spring and fall. I would just urge you to consider that. Okay, I think it kind of gives a different view to networking overall. So, the demand for radio frequency is just exploding, right? But there's no additional spectrum, so we got to learn to share spectrum. So here is a spectrum sharing architecture, you guys, and I'm going to end with this. You guys, of course, there's lots of details in this, and I think, if you wanted to get deeply into this, that would be the stuff that you would be interested in. So you guys, in the lower right, I'm going to start off with a couple pictures. I got to get my mouse over here, gang. There we go. In the lower right is Hat Creek, right? And so we have this deployed at the Hat Creek Radio Astronomy Facility. And again, we've got these sensors that are in this little box, and that little box there on the lower right, there are 8 of those set throughout this area. And all we're doing is looking to detect any interference from cell phones, from Wi-Fi, from any RF emitters that are sending energy across that facility that's going to impinge upon those telescopes. So we use those sensors to detect RFI. The other thing we use those sensors for is we determine the noise floor. What is the noise floor, the lowest energy in that particular RF band? Because then if you know what the noise floor is for any band, then if you see energy above that noise floor, you have a signal, okay? So we use those sensors to do long-term longitudinal studies and establish the noise floor from, we go from 300 megahertz up to 12 gigahertz, okay? And so we've got the noise floor established in 20 megahertz increments across that. And so whenever we see a signal go above that noise floor, we know we've got a signal transmitting across that facility, okay? So that's part of it. And when we detect interference, we can give real-time alerts, okay? And so what is that doing, you guys? That's characterizing the spectral environment on the Earth's surface around that radio astronomy facility. And then once you've got it characterized, you can detect when interferers are transmitting energy across that facility. Think of Wi-Fi, think of cellular, etc. Think of a walkie-talkie. It's just electromagnetic interference. Okay, so that takes care of interference on the Earth's surface. But there is a great equalizer for radio astronomy facilities. Radio astronomy facilities, you guys, are typically located in nowhere. And there's a reason for that. You don't want a radio astronomy facility next to New York City, right? You're just going to have all that RF energy spewing out across the city. So by just that simple observation, radio astronomy facilities are typically in very remote locations. They try to get away from everything they can, just so they're not subjected to that RFI. But the great equalizer, you guys, for any place on Earth, even if you're in the middle of the Sahara Desert, if you're in the middle of the Atlantic Ocean, is satellites, right? Satellites are continuing to go over the top of us. I mean, in LEO orbit, low Earth orbit, which is 200 kilometers to 2,000 kilometers above the Earth, there are over 20,000 satellites, right? And so those satellites are always, just think of that satellite coming across the top of the HCRO RA facility, right? There's its ground path. And if that satellite is transmitting to a ground station, and the frequency of that transmission is what the radio telescopes want to observe in, then that's going to ruin the radio telescope observations. And this happens all the time, right? There's 20,000 telescopes. Certainly they're downlinking to different ground receive stations, but satellites are always coming over radio astronomy facilities and really corrupting and ruining their observations. So what we've done is, we've put together a database. We've got, these are their cell towers, the FCC, right? The Federal Communications Commission. ULS is unlicensed service. Actually, no, it's the licensed service, I should say. So any emitters, any RF emitters are in the FCC database, and their transmit frequency. You also know their coordinates. So every cell tower is in that database, guys, is the way to think about it, okay? And so what you can do is you can understand where those cell towers are at. And then if you're able to control what frequency those cellular systems are transmitting on, you can change their transmit frequency and make it a different frequency than what the radio astronomy telescopes are observing in, okay? So that helps, get rid of any ground-based interference, okay, that are licensed. You do have rogue emitters, and our RFBS sensors will catch the rogue emitters. Well, really, it's the same thing for satellites. right? Once a satellite is up there, it's up there, right? It's, you know what its orbit is, and you can very accurately, I mean, very accurately determine where that satellite is in time. And so that's called, orbital mechanics. The characteristics of the satellite orbit is called the orbital ephemeris or ephemeri data. And that's all available at spacetrack.org. So the United Nations and the US Space Force, typically all entities in the world, quite honestly, now certainly some defense satellites are not going to be in that database, right? And that goes for the US, that goes for any other country. But here's the thing. If you see a satellite going over the top of you and it's not in the database, and then you see it again, then you know its orbit. You're actually able to compute that, okay? And it's like, okay, well, you're not in the database, but I know you're up there because I've seen you go by twice. So what happens is that if you know the satellite orbital information, right? What its ground path is and what it's crossing over at any particular point in time, and you know the frequency the satellite is transmitting at, right? It's transmitting information down to ground. And you know the location of those ground stations, right? If you know that information, then you can use that a priori known information to compute satellite-free observation windows. How it works at the radio astronomy facility is they'll say, let's just go back to the 1420 hydrogen band. Hey, on September 2nd, tomorrow, from 0800 to 1700, so for 9 hours, I want to monitor the 1420 megahertz band. And so they just put that little reservation request into a portal, okay? And so now we know what that radio astronomy operator wants to do when he pushes, please verify I can do this verification. Then you know where they want to, the time and the frequency that they want to sample in, and you can determine by orbit calculations, you can determine all the satellites that are going to come across that facility over those 9 hours, right? And so that's how you do this, is you figure out what satellites are coming over, and if any of those satellites would be downlinking in that 1420 megahertz band, you let the first, you can do a couple things here. What we're doing with SpaceX and Starlink is we're actually having SpaceX and Starlink change their downlink transmit frequency when they are over that Green Bank telescope, that big one I've seen before. So we can make them change their frequency here. It's actually easier, honestly, just to let the radio astronomy people know, hey, if you're going to sample from 0800 to 1700, either that's an absolute satellite-free window, or you're going to have potential corruption at a specific time because when those satellites are coming overhead. Okay, so what does that do? That gives you, using spectrum sharing methods, that gives you dynamic protection of terrestrial RA facilities as they are doing their observational scans looking back in time. And so really, we've solved the problem here that will work for any radio astronomy facility. It would even work for the shielded zone of the moon on the backside of the moon, okay? And let's take this one more step. Okay, now Starlink, right? You guys, Starlink and OneWeb got these constellations of satellites, right? There's not just one satellite. They've got these constellations, from 700 satellites, which I think is Kuiper and Amazon, to Starlink, who wants to put up like 4,000 of them and has got several hundred of them up already. And in fact, my wife, how do I want to say this? I guess, my physical connection, my backhaul to the university for this is actually going over Starlink. Starlink is actually pretty good. But from a spectrum sharing perspective, you guys, what can happen is, with all these satellites up in orbit, and these satellites are not only downlinking the ground, right, which is what we've been talking about before, but now with this constellation, these satellites are relaying data. There's a satellite, maybe it wants to send over to this satellite, and then it gets relayed to ground. So now you can just think of a bunch of cross beams, right? It'd be kind of a nice analogy in space as those satellite constellations are shuffling data back and forth and then going to ground. And so that's another capability for spectrum sharing. EESS is the Earth Observing Satellite System. And those are the satellites that do the weather prediction and crop moisture and et cetera. Okay. And, ultimately, this is a nice diagram of what, I guess, an artist rendering of what a satellite constellation might look at. So overall, you guys, what we've built the spectrum access system. Okay. And this really is a geospatial temporal coordinator of satellite transmitters. And when we know that information, and the time that a radio astronomy facility wants to make an observation, then we can compute, hey, is that going to be a satellite-free observation window? And then from that, you can go to the control room and then point the telescopes where you want there. So you guys, this overall is about spectrum sharing. More than anything, I hope you guys start to realize the need that this is a critical resource. It is renewable, but it's not infinite, right? We really have allocated that spectrum. And when you've allocated that, what that means is, hey, it's been licensed, right? To all the cell phone users, right? They're spending billions of dollars, T-Mobile, AT&T, Verizon, billions every year, hundreds of billions of dollars to get those licenses because they make that money back with, their cellular phone business. So this, it's a huge amount of money. There are economic, sides on, there's economics to think about because broadband is a key indicator of, a GMP or economic well-being. And so if you're able to increase broadband utilization, but also protect passive observers such as Earth observing telescopes or radio astronomy telescopes from interference, then really you're helping a lot of things here, right? Important areas, economy, security, military type of operations, and then of course the cool stuff of looking back in time and figuring out, how the universe formed over the last 14 billion years. So I don't want to, this is the work I'm doing. You guys, there are a lot of interesting things to do here. Spectrum sharing, RF propagation modeling. It turns out when you're looking through, a minimum of 20,000 satellites from a search space problem, you get into some algorithmic efficiency because you've got such a search space that you have to make things very efficient. Okay. Another thing is so let's take this one more step. And how do I want to talk about this? Let me go back to this previous slide. How do I want to frame this here? I'm thinking about this because I was just kind of, I guess, freewheeling here a little bit. So think about the spectrum access system that we got. And let's say we've got two users that want to use the same band at the same time, right? And and right now this really is geospatial temporal frequency sharing. We're not using one particular band to multiplex multiple users across. But this would be a common occurrence, right? RA wants to use a band, cellular wants to use a band. Who gets to use it? Okay. And so what we want to do there, you guys, is we want to take advantage of blockchain and smart contracts, right? So we're going to know all RA observation schedules, right? We're going to know what people want to do. We're going to know, what the interferers are. And what you could do with an automated blockchain system is you see two requests come in to utilize spectrum in a certain area, and they're going to conflict with each other. But then you could use something like smart contracts to do some automated negotiating between the two users to, in an automated fashion, figure out who gets to use that spectrum, right? Not call in the FCC or the NTIA, but do it in an automated fashion. And so, blockchain with the distributed database is actually quite nice for that. And, of course, there's great ledgering capability. but blockchain has got some characteristics, including, what I just mentioned on the distributed database, that make it attractive to do that automated spectrum negotiation via smart contracts within blockchain. So I wanted to call that one out specifically. You guys, there are other, deep CS and deep EE research opportunities here. So overall, gang, we're about the top of the hour here. Let me wrap up. This really applies for any faculty member you guys might want to interact with. You can do so via independent study, and for me, it would be spectrum related or space communications related. But for other faculty members, it's going to be the research they're doing. You also can do, a 6 credit hour MS thesis, right? I know MS theses are not quite so popular, but both of those are, academic credit opportunities to work on research activities with myself or with other faculty across the university. Right now, I've been fortuitous to get some, let's say, big NSF awards here. And I say that cautiously because anytime you're on the upswing means there's going to be a downswing. So right now, very sustainable. We've got several opportunities to do this research out at Hat Creek and at other radio astronomy facilities across the United States. I have some hourly opportunities where you could be a test engineer or an operations engineer and come up to speed with what we're doing, and then start participating in, kind of deeper research topics, say blockchain as an example, or, writing those algorithms that's going to parse all those satellites and doing that in an efficient manner. Definitely computer science, algorithmic heavy type of topics. So we have a test engineer, an operations engineer, an ops engineer, and the test engineer both would do a bunch of these surveys around the University of Colorado. And we are also doing this with NIST and NTIA at the Boulder Commerce Center there on Broadway. Okay. I also have got several GRA positions, you guys. And, this is 2 to 3 years of funding. Right now, I've got 2 positions open, but I'm anticipating more positions. You guys, I'm a little bit of a stickler about this. I'm not just going to give an RA to somebody that I don't know. And so the way I do this is I ramp people on, right? I ramp them on as hourly researchers. I make sure you get a fair wage. I'm actually very ethical about that. And, you can start out as an hourly researcher for 15 or 20 hours a week, or maybe, 10 to 15, depending upon your schedule. And then if it looks like you're going to be a good fit for our team, then really, I pick you up for 3 years of funding for your PhD or to finish your MS studies. So that's the project. There are opportunities with me, like I'm sure there are opportunities with other faculty. If you're interested, send me application materials. Or if you want to set an appointment and stop by my office and just chat with me about the opportunities, you can send me an email. I think I've got one last slide, and then I'm going to open it up for questions. So you guys, this is something that I'm doing here in March of next year. I've long been working with NASA on space communications, and I've worked with NASA to make LTE, 3GPP LTE, is going to be demonstrated on the lunar surface. And really, this is the candidate architecture for Artemis, the program that returns people back to the moon. Artemis 3 will be boots on the moon. Artemis 5 will be, a couple years later, and they will have a rover that will go 10 kilometers away from the lander, et cetera. So to prove that the LTE communication systems are going to work, that launches next March, and it's Nokia Bell Labs, and I just call it LTE on the moon. So what will happen is the lander will be at the South Pole. They're looking at landing locations right now. And then when the lander lands, then out, a little hatchway opens and out goes this rover. And this rover is going to go 2 to 3 kilometers away from the lander. And the idea, the rover's doing a bunch of science, it's also doing communication verification. And then I'm using it to verify that LTE is going to work on the lunar surface. I have no doubts, but you still have got to verify that. So what we want to do, you guys, that Hat Creek Radio Astronomy Facility, that's where SETI is, the Search for Extraterrestrial Intelligence. They're actually in the same building there. And also, for those of you that know about GNU Radio, which is open source software-defined radio, that's also at that Hat Creek facility. So this is actually, over Northern California. And here's LTE on the moon. And what we're going to do is we're going to point those 6.1 meter telescopes. We'll point a couple of them at the south pole of the moon, and we are going to pick up the communications between the LTE lander, which is essentially a cell tower, and the rover, which is essentially a UE. Okay. And we will, without a doubt, you guys, radio astronomy telescopes are so sensitive, there's no doubt that we are going to detect that signal. We think we might even get to the point of being able to demodulate the signal. And I know the people at Nokia Bell Labs, if we can demodulate the signal, of course, LTE, 5G communications are all encrypted, right? So, but if we could demodulate it, I could work with Nokia Bell Labs to get that decryption key, and we could prove that we demodulated all the bits correctly into a well-formed file. So that's all spectrum, right? And while this wasn't spectrum sharing per se, it really shows, how much spectrum is used overall, right? Whether for science, for communications, super important on the Earth. I think knowing something about wireless in general, just from an introduction perspective, is important. So I'm going to stop there, and really, I'm just going to click back to this picture here, and I'm going to open it up for anybody that has any questions that you would like to ask me. Any questions from the crowd? I see we got 27 participants. Thank you guys for joining in. Hey, it's already September. And by the way, best wishes for a successful academic semester. So we got Ash Kit with your hand up. Please go ahead.
Hey, Professor, thanks for the presentation. It was really interesting to learn what you have been working on. So one question that I had was, can you explain again what kind of work are you trying to achieve through blockchain, for example? That was something that caught my ear, and
that's fine. So think of, there's a radio astronomy facility, and they schedule those telescopes, right? Each one of those telescopes are scheduled. Hey, I'm going to point it at this location in the sky, and I'm going to be looking for this potential RF band, and I'm going to do it for this potential amount of time. And so that all is known a priori, right? You just don't freewheel those telescopes around. They're big. They take a long time to move. So you know what you're going to do. So just think of, hey, I've got a bunch of reservations, all the different radio astronomy telescopes want to use, okay? And then think that there are some other users, such as a cellular user. Band 3 in cellular is at 1800 megahertz. That's a very popular band in Europe. As it turns out, it's not so popular here in the United States. But what if those telescopes, wanted to do, an observation at 1800 megahertz, and the cellular system also wanted to be able to use that band, okay? And so now the reservation system knows that you've got multiple users that at a specific geolocation want to use the same frequency band, right? And that's all in that database. And so what you could use blockchain there is you detect, I've got two users that are going to conflict. I can only give one of them the spectrum allocation. And with smart contracts, you could, which is a blockchain facility, you could, in the smart contracts, put down some, let's say, rules and steps so that you could have the two competing users that wanted that piece of spectrum at that geolocation. Using blockchain and smart contracts, they could do some auto negotiation with the information in their smart contract, definition. And, the result of the arbitration would be, from the smart contracts and blockchains, the outcome would be one of the users would be chosen. So what's nice about that is you've got that information in a database already, right? And if it's blockchain and distributed, you've got a more resilient database. But now I'm just going to use the idea of blockchain and smart contracts to auto-negotiate who gets to use that spectrum, right? We're removing the human in the loop, and where somebody decrees, okay, in this scenario, T-Mobile gets to use that spectrum, or in this scenario, the radio astronomy facility gets to use that spectrum. You could have information encoded in those smart contract representations that allows a computer to automatically negotiate, right, and figure out who gets to use the spectrum. That's the attraction of smart contracts and blockchain there. Does that help?
That does help. If I may ask, can I ask a follow-up question on this?
Sure, go ahead.
This contract that you're talking about, is this like a temporary contract, or is it like something binding that, as you mentioned, like let's say T-Mobile, right? They have some band allocated to them. So is it like flexible that T-Mobile can also stop using that band at some point and then somebody else comes in?
Well, that would be the idea to, optimize the utilization of that particular band. And if there is, conflict, multiple people wanting to use that band at the same time, then you're using the blockchain smart contract capability or facility, I should say, to autonomously or programmatically determine who's going to get the band for that particular time. And so, otherwise, who's going to resolve that conflict, right? Right now, nobody resolves it. You just interfere with each other. But if you also can get into a scenario where, okay, I know we're going to be wanting to use that same band at that same time, and you may have to adjudicate who gets to use that band with the FCC. And so, that's what the FCC Enforcement Bureau does, is that when they see people illegally using spectrum, or they've got two people that are competing to use spectrum, they resolve and adjudicate that like in a legal court of law, right? But if you got to the point that you could codify priorities and, potential negotiation tactics in the smart contract, then you could do that automatically. That's the attraction there. Automated spectrum conflict resolution would be the sentence there. And thanks for making me say that pedantically precisely.
Thank you so much. That helps.
Okay, I see somebody else with their hand up. Please go ahead. Nope, maybe I didn't. Okay, other questions, gang?
Yes, I have a question, Dr. Gifford. You hear me?
Please go ahead.
Oh, are there two of us?
No, I believe it's just you. Go ahead.
Oh, just me. It was breaking up a bit.
So your audio is coming across chewed up. Can you try and say it again, or move a little bit, or put it in chat?
Yeah, let me go out here and see if this works here.
You know what? As you were moving, that changed it, and I hear you much better. So go ahead and ask the question, my friend.
I wanted to introduce myself. My name is Aaron Hayden. I'm a first-year master's student in the TCP program, and just want to say it. I've talked to a lot of people recently, and it's clear you're really passionate about what you're doing, which is pretty damn refreshing, I'll say. Also, last few weeks, I've been interested in, I guess you'd say, sensor detection, like signal detection, all different types of wireless detection stuff. So I've been researching how to do that a bit. Not to get into too in the weeds technical question. It's just been something on my mind for the last few weeks. But how do you store the data with the vast amount of data that you created? I think you said, did you say Hellerman field? And whatever that field was, where you created that, for lack of a better term, triangulated area that was capturing all that sensor data coming through. Right. Where do you store that, and how does that work?
So that's a great question, because you got, when you're sensing spectrum, really what you have is the way it turns out, and I won't go into explanation, you guys, I'll just make a couple statements. It's called IQ data for in-phase quadrature. And And when you are sampling that data, and you really are typically sampling that at 20 or 30 megahertz per second. So 20 or 30 million samples per second, right? That's your typical sampling frequency there, guys. And what happens is you just generate reams and reams of data. So there are many strategies here. You actually can generate too much data. So one thing to do initially, you heard me talk about establishing the noise floor in a band, right? So once you establish that noise floor in a band, right, it's at some power level, then you can just sit there at the sensor and sample, right? And as long as it's at or below the noise floor, there's no signal, dump the data on the floor. There's nothing interesting. But as soon as you see that signal go above the noise floor, then you start grabbing it, right? So that's one method. There's a bunch of other stuff to do here, you guys. Honestly, I think when we were, you guys, I'll do it like this. If I go back to this right here, the data for one of these plots is really on the order of hundreds of gigabytes. So there's definitely a data handling problem here, and you need to be able to filter at the sensor. Okay, is rule number one. And certainly, if you're not detecting a signal because you know what the noise floor is, then you just don't record. The other thing is that if a signal is not intermittent, and most signals, either you kind of get them one shot or they're just there. So if the signal is just there, well, you don't need to record it for 60 seconds. Typically, what we do is we record for 1/10 of a second and then wait for 1 second to write all that information to disk. Then we move to another band or we sample again, right? So there are some different strategies there to handle all of that data. But that being said, my friend, at Hat Creek and at CU Boulder, to handle all this data we've been generating, I had to spend $22,000 for an 800 terabyte storage server, 800 terabyte, almost a petabyte. And we're going to be managing all of that data, but you're right. I mean, that is kind of a level zero problem, and you need to understand how you can reduce that data at what points in the data acquisition chain. And if you would like to chat about that more, Aaron, I'd be happy to in my office or over a Zoom.
Great. I'll send you an email after this call.
Great. Thank you. All right. I see. Is it Kurt Honker? Do you have a question?
Yeah. Hi. Am I
Hello.
audible? Can you hear me? Am I audible?
I can hear you fine. Please go ahead.
Yeah. So I had one confusion about spectrum sharing. So from what I know about for example, in telecommunication, so if, for example, 5G base station uses 4G spectrum, we call that spectrum sharing. But from your presentation, what I gathered, I guess I'm a bit confused, is that do you mean that if we don't use the same time and frequency resources, are you saying that is spectrum sharing?
There are some different, so that's a good question. Let's say different types of spectrum sharing. So good question. First of all, when we talk LTE and 5G, and they talk about DSA, dynamic spectrum sharing, that honestly is really not spectrum sharing. It's just, if you're using 5G, you can have some LTE resource blocks, and you can, use some LTE spectrum. So 3GPP, you kind of just reused the term spectrum sharing because it was becoming really popular. And what they were saying is, hey, if we've got, some LTE spectrum and some 5G spectrum, our 5G base stations are now smart enough to use both of those spectrum bands. Okay, so that's what spectrum sharing is in cellular 3GPP. Okay, the next one could be, let's say, temporal, right? And the system that I've been talking about right now is really temporal sharing. I didn't use the fancy word word geospatial temporal, but all that is, geospatial is just a certain point, right? So the certain point could be in space, could be on the ground, right? It could be an orbiting satellite, or it could be at a radio astronomy facility. So at that particular geospatial location, Hat Creek Radio Astronomy Facility, right? And we've got all the spectrum available. What we do is we manage all the users of the spectrum so they are not transmitting in the same band at the same time. So that's geospatial temporal spectrum sharing. Okay. Now, the next step, right, is when you have altered your physical layer protocol, right? Something like OFDM, is really what Wi-Fi and LTE and 5G all use right now, where you can take and alter the modulation in that channel such that you can have two different users in that same wireless channel, and those different modulation schemes are coexistent with each other. And that's definitely a harder problem. So does that answer the question? Because that's a very nice observation. There are different types of spectrum sharing. This is not, the simple 3GPP kind of PR play on spectrum sharing. This is geospatial temporal sharing, managing multiple different users and multiple different sources, but you're managing that spectrum use in time at a particular point. And, that comes down to a database command and control system, right? You know all the users, you know what their requests are. This is an optimization algorithm, operations research, really. And then, the next level, and this is work that, other people are doing as well, is, okay, if I've got a frequency band and I know that frequency band is 100 megahertz, right? Can I have two disparate users that are potentially using different wireless protocols, let's say, Wi-Fi and Bluetooth, in the same channel at the same time? So that Wi-Fi Bluetooth example is really spectrum sharing with different system wireless coexistence between the two systems. So that's the more advanced spectrum sharing, and that one is harder to do from a five-layer perspective. So great question. I hope I answered that. And do you have a follow-on? Does that suffice?
Yeah. That was very helpful. I understood the points. Yeah, thank you.
Well, thank you. I'm glad that I didn't convolute that too much. Sometimes I can talk too much, quite honestly. Okay, gang. Well, look at, really to all of you, thanks for joining in, and, the best of luck to you as you're doing your studies at computer science. You guys, I'm just going to make one more unabashed, plug. You guys think about taking that Introduction to Wireless course. I think every computer science graduate student should take that course, right? Because wireless is so important. It's not saying you're going to become a down-in-the-weeds wireless engineer like me, but it is saying you will know about the basics of wireless communications. And if you are in computer science or a network engineer, I think that fundamental knowledge will stand you in good health. All right, with that, I will close this session out. Again, you guys, what I'll do here one last time is just click to this slide. If you've got questions or want to stop by my office, I'm on the 6th floor in the computer science, in the engineering center, 6th and 7th floor computer science floors. Stop by my office or send me an email. If you've got interest in academic credit or potential funded opportunities, and think that, you've got the skills to work with me, I would love to, talk with you. And I always kind of go through this initial vetting, you guys. I'll say to all of you, if you're going to give a student, essentially $150,000 to do their PhD, well, you can't just walk in and say, I want to be a GRA, right? You need to prove yourself to the faculty member. And the best way to do that is to interact with them. And oftentimes, the number way to do that is to be conversive in a class and start talking with the instructors. So I do have all these opportunities, and I probably have more. But just, don't think that without coming and talking to me and demonstrating to me your passion, that I'm just going to hand out an RA. Just be reasonable. Your approach approach it like you would any job, do the recon, reach out and talk with the faculty and the researchers on the team and show that you're going to put in, let's say the appropriate effort to learn about the position and then do the application. But I really truly do have all these positions. I probably will have a couple more PhDs in over the next year. So if you guys are interested in this particular work and would like to investigate this opportunity more, please let me know. And you guys were 9 minutes past, and I need to break off really for everyone's I guess respect for everyone, including Rock Street, gang. So send email if you got additional questions, and thanks everyone for your time.
Thank you, Kevin. We
Have a
appreciate
great
it.
evening, everyone.
Bye.
Bye now.